Now our next speaker is Niels Peinert from the University of Ghent. And while you pull up your presentation, some longer time ago, Jens was still in Delft, a master's student working on vertical takeoff and landing of airborne wind energy systems. And he later became a PhD student in this Airborne project. So it's also nice to see how young talents are moving around and picking up opportunities to continue their academic careers at different universities. So it's really nice. Go on.
Yeah. Good morning, everyone. Thank you for the introduction, Roland. So in the coming 15 minutes, I will explain part of my PhD research with the title Unsteady aerodynamic simulations of an airborne utility systems in the realistic flight conditions using CFD. So airborne wind energy is an emerging wind energy technology, as we all know, and we fly crosswind patterns to convert the wind energy into power, as you can see here on the slide. And these systems have been found to be very subjected to unsteady aerodynamic phenomena. These trajectories you fly are, there are differences or variations in velocity, angle of attack. We also have transition between wheel in and wheel out, so this maneuver causes the aerodynamic loads to change in time. And the goal of the work I present today is to present a framework that allows to simulate this maneuver in a CFD environment. There are other sources of unsteadiness. We can have fluid structure interaction, where the movement of the structure causes aerodynamic changes, turbulence and gusts, and wakes. I will not talk about this in this talk, but the model is developed such that these can be taken into account as well in a later stage. So let's dive into the methodology of this framework. So I start from a reference aircraft developed at TU Delft by Dylan, which is envisioned to have power output of 3.8 megawatts with a wing area of 150 square meters and a rate of around 7 knots. So we developed an aerodynamic model of this aircraft in CFD, so in Fluent. And this model features separate C meshes, so structured mesh, around all the lifting bodies. So we have a C mesh around the wing and the tails, and these are connected using the overset connectivity, as I will explain in the next slide. Also, the mesh has been designed in a way that they are valid to operate using wall functions. So this is what connects the meshes. So this is the C mesh of the main wing, and here we see the C mesh of the tail, and that they overlap here, as you can see. So this is a side view, and this method divides the cells and will give certain types to certain cells. So we have the green cells, and these are just solved as in a normal CFD simulation. Then we have in red the donor cells, and at these cells we interpolate and pass the flow data to the blue receptor cells of the other mesh, and vice versa. And this is how we interchange the flow data between the different meshes. So in order to simulate the movement, I really applied a motion to the aircraft mesh, and it's basically flying in a background mesh where I simulate the wind physics. And so for the work I present today, I applied a uniform inlet velocity of 10 meters per second, uniform pressure at the back, symmetry conditions at the walls, and then a slip wall to conserve the uniform flow. But note that in later work, we can adapt these boundary conditions to also include, for example, a logarithmic profile or turbulence at the end. So then we have several overset phases, so I already explained the methodology, but there are different connections. So there are levels of overset connectivities. First of all, between the background and the main wing, and then between the main wing and the horizontal tail, and then in the horizontal tail we have connection with the deferred elements. The flow physics are solved using incompressible unsteady rounds, using time step of around 0.01 seconds. We use the k omega SST turbulence model and first order schemes in space and time. Generally, it's recommended to use a bit of higher order schemes, but at this point, the quality of the mesh does not yet allow proper convergence. So that's why for this proof of concept, we use first order schemes. Then, of course, we need a trajectory to implement, and this is done by using Airbox. So in Airbox is an optimal control problem that optimizes trajectories for certain aircraft configurations and constraints. So in this Airbox, we define a system dynamics model of the megawatt aircraft. This is a 6 degrees of freedom model. It assumes a straight tether. And to calculate the aerodynamic forces in Airbox, there is a simplified or an analytical aerodynamic model given by this equation. And so basically, it's lookup, or they're based on functions of the force coefficient as a function of the angle of attack, side slip angle, the roll rates, and also the control surface. Okay, so important to note here that for the analytical model in Airbox, we do include the control surface deflections, but this is not yet implemented in the CFD model. This is for later work. And the stability derivatives, so basically these functions are based on a vortex lattice model of the megawatt. So then we let Airbox calculate an optimal trajectory, and this is defined by position in time, velocity, angular velocity, and altitude. Yeah. This is basically this trajectory, and then we apply the motion to the full aircraft mesh, which is freely moving in our stationary background mesh where then the wind flow is. So I will show now some results, but of course I have to show now with some cautions. These are some initial results. We haven't done a very detailed study on grid dependence or on a turbulence model, so keep this in mind, but I think they're already quite promising for future detailed studies. So this is what the trajectory looks like. So it is constrained by a 4-loop power cycle, where in the last loop we also reel in the aircraft, as you can see here, and the complete loop takes around 75 seconds. In red, I also indicated the zones where we have negative power. So we see that, of course, during reel out we have negative power, but also some parts during, or reel in, let's say. This is due to the fact that we need to get the aircraft back. So this is what the power profile looks like in time. So I plotted here the power prediction of Airbox in the dashed black line, and then in the dashed blue line we have a power prediction using the aerodynamic forces of the CFD model. So the dashed line is only the wing, the wing, and then the solid line is the complete aircraft. You see between the wing and the aircraft there's not much difference, but less with the full aircraft due to the extra drag. But there is some difference between the Airbox prediction and the prediction using the aerodynamic forces, and this is because when we look at the force coefficients of the CFD model, we predict less lift and more drag. And so I plotted here the lift coefficients and drag coefficients of, again, the Airbox model, CFD, both wing and aircraft. And you see that the CFD model predicts less lift, less performance of the aircraft. Now, small note, I had to, of course, deactivate the computational controls to properly compare the aerodynamic forces here. So that's why I said here, no control. Also, the wing is a bit, the full aircraft has a bit more drag than the wing, and it also stops here because at this point the simulation is still running. As you look closely, it's still marching in time. So if you're a bit patient, maybe by a few days, we hope, yeah. So probably why we would predict less lift is we look at the velocity magnitude. We see some blue zone here, which indicates that there might be separation at this operation point. Again, to really have proper results or to be confident, we need to do some more detailed mesh studies, but this already gives an indication on what's going on here. Then, of course, these CFD models are quite computational expensive, but we also get a lot of data from it, which you can use for both quantitative and qualitative analysis. I plotted here the pressure distribution on the full aircraft for 4 positions in the loop in a direction which is perpendicular to the wind, and so in the x direction. You see here that during flight we have varying pressure distributions. Also, you can see the asymmetric distribution. You have some more pressure here due to this rotational motion. Indeed, and then I want to end the presentation or the results sections with a visualization of the wake. I have plotted here the weighted vortices using the Q-cut theorem, and this is actually flying now in real time. So I hope one day we will see this as well in reality when we have some big smoke guns on the aircraft of the guns. So we see that the wake force, of course, follow the trajectory, but then march in time. Okay, so to conclude this presentation, I presented the proof of concept for a framework to simulate airborne trajectories in a CFD environment. For this, we used the overset technique, and this has been proved to be quite robust to do this, and showed some promising initial results for future studies. Then an outlook to future work. So today I presented actually a one-way coupling from the system dynamics to the aerodynamic model. But in later work I also want to couple the forces back to the system dynamics. And also make a coupling with the structural dynamic model, which was already established in previous work. So the overall goal of this research is to develop a high-fidelity aeroservo elastic model together also with my colleagues in Ghent University. So thank you for listening. I'm now open for any questions.
Thank you, Niels, for this interesting presentation. It's interesting to see that there are already some tools developing as primary choices, Airbox more as the trajectory planner tool, and then MegaWest, for example, as a flight control tool. I think that's really interesting that there are already some good candidates out in the field for future researchers to actually use these tool chains for increasing the productivity. Are there any questions?
So it seemed that the coefficients in all blocks were maybe not the same in the CFD simulation, and then you ended up with a different control loop. I'm curious if you extracted the coefficients from the CFD and then you plugged it back into all blocks, did you get a different trajectory solution, and then would that kind of improve the flight in the CFD simulation? Have you tried? I can see you're still running simulations, so maybe you haven't had a chance to look at that. So.
Well, that's definitely a very interesting issue. As that's indeed the way we want to go is to get the aerodynamic forces of the CFD model back to the dynamics, and then indeed see would there be another trajectory, or would the trajectory would it still be able to fly the trajectory? Then we need another trajectory. So these are indeed some interesting questions for the future.
Are you planning on sort of when you talked about a bit of an aerostructural sort of, are you planning on sort of an iterative process where you sort of like continuously update the coefficients in sort of all blocks? Because all blocks solves entire trajectories, so you'd have to, I don't know if you, something like that, or?
I don't really understand the question.
So you get a different trajectory from all blocks, and then you apply it in your CFD, and then you might see that the coefficients are a little bit different. So there'd be this sort of circular dependency between between the two? Were you sort of thinking of setting up I'm just trying to understand sort of the future work. Were you sort of thinking of setting up a iterative scheme so that one can do trajectory with sort of high fidelity?
So I think there are two approaches here. So I think what we can do is to tweak our coefficients, which are already in our books, with data of the CFD, and then get already more accurate predictions of the coefficient that we will have when flying the real trajectory. Because what indeed may happen if we don't do that, and we try to fly this trajectory with the forces from CFD probabilities, we might not be able to fly this trajectory because it's what was made indeed on aerodynamic coefficient that overpredicts CR. So indeed that's something we need to be aware of in the future, and it's also something we will look into to tweak a bit also the inputs of our books itself.
Just follow up on this, but probably also the coefficients will change according to where you are in the trajectory, right? Because if you are at the beginning of the trajectory, then you just have the starting point of the wake. At the end, you will have a kind of fully developed wake, so probably there are some tricky parts there. And that was my kind of question related to that. The coefficients you showed are at the beginning of the trajectory or after?
This is when starting like the loop from zero.
Okay.
And then flying one full power cycle.
Okay. Yeah. So there were
A related question to again the trajectory. So I see that when you showed the wake simulation for the second loop, I think you are already in the wake of the first loop. But then in our box, can you tune it in a way that you increase the radius while drilling out? Would there be a good trade-off there to get out of the wake of the first loop by constantly increasing the radius while drilling out, and then you get out of the wake?
Well, then our books needs to be aware of this when generating the trajectories.
Yeah. I mean, if you see like the wake is affecting a lot, maybe there is a good trade-off to increase the radius and then get out of the wake.
Yeah, exactly. That could be a good strategy to mitigate this effect.
Thanks for the very nice presentation. Just a curiosity here, how expensive is this? Because OSM mesh is not.
What was the last?
OSM mesh is like, at least for us, quite expensive. So
yeah, it's indeed quite expensive to put a bit of numbers. The framework I showed here uses a mesh of around 20 million cells. And on, if I go back to the power slide, or the forces. So to do one loop, this was done on a supercomputer with a bit more than 1,000 CPU cores. And one loop took 3 days on the supercomputer for the wing, and that was then able to do a full loop. But again, these 3 days were not enough to do the CFD for the full aircraft. So there I would, need more than 3 days. I would, based on the profile, I would say then 6 days. So I'll step out with the lead.
and that's even with a coarse mesh.
Sorry?
And that's even with a coarse mesh.
It's indeed even with a rod, because indeed for the wing we use like wall functions, so we could go much finer there. But again, I mean, there's still a lot of room for improvement. I actually have a rather big background rig. Also, the mesh of my tail is quite fine compared to it's actually the similar mesh as my wing. So I could do a lot of optimization there. For example, if you really want to focus on the wing aerodynamics, maybe refine a bit there and then a bit coarser elsewhere where a bit less interested in results or where it's less critical. So there's a lot of room for improvement also in the mesh itself. But indeed, there will always be very expensive pieces of mesh. So
Thanks.
thank you for that comment.
Save some for the next person.
Any other questions?
Sorry, thanks. As a control person, how important should we be that flying into the wake again? How much impact does that have towards power generation? Is that something that we, as control people, really need to be taking into account, or is it really just like small percentages that will affect it?
And for this simulation, I haven't really seen the effect, because of course it's only one loop, and you probably see the effect when you get more loops. So I hope to answer that question at some point. For now, I would. There has been studies on on wake analysis by my colleague Thomas Haas. So I think if you want to have an estimate on the power reduction, I would talk with him. I would say that in future it would definitely be interesting to take into account this controller. And also the interesting part with Airborne is that we can actually do this. I mean, we can avoid it because we can steer it in every direction. And I think this might also have an impact on the overall power or the performance.
Well, thanks.
Thank you very much, Niels, again.